Okay, so today's topic is transformers, which is chapter 23 in the book. Okay. But before we really get into transformers, what I want to do is talk about why we care, why these things are so useful. So let's take a look here at the find my correct. Oh, must be this one. Okay. All right. So I just want to remind you, I guess, to start off with, back in DC circuits, one of the first things that we talked about was simply looking at the resistance. All right. And so if you remember, see how my drawing skills are today. All right. This is weird. Keeps jumping on me. Um, all right. So if you remember from DC circuits, to calculate the resistance, right, the actual resistance is due to the physics of the device. And so we had this term rho, which was the resistivity, and then we had the length of the wire divided by the cross-sectional area of the wire, right? So the rho, right? This is the Greek letter rho here, and this is what they refer to as the resistivity. Okay, so they talk about the resistivity, and the resistivity is due to the makeup of the material. So one of them we talked about was just copper wire. So the resistivity for copper wire was something like 10.37. Okay. And then the units of that was like ohms times circular mils divided by feet. Okay. So that when you multiply times your length, um, so when we multiply times the length here in feet, then that'll cancel out. And when you divide by the area in circular mils, then that would cancel that out. And then you're left with resistance, right? Ohms. Okay. So I just kind of wanted to start off here by reminding you about this. And then the, okay. So given that, let's take a look here at an example. Okay, so this is an example here of, we have over here our power station generating electricity. Okay, and so these guys are generating electricity and they're going to feed that to my house. Okay, I'm using this as an example because when I first bought my house, I had a 100 amp breaker box in the house. Coming in from the power, I had a 100 amp box, and I actually tripped this more than once. Okay, we have uh, electric stove. We have electric water heater, and at the time I had this like massive laser printer that I was using to print out papers and stuff. So plus all the other things like TV and all that. I don't know. So it's a couple of times there we actually tripped this 100 amp breaker. Okay. So I just want to do an example here. So we know, and I've kind of simplified it a little bit here. So what I'm saying here is, over at my house, I have 100 volts. Now, really, right, it's more like 120 volts, but so we're going to say it's 100 volts RMS. You know, because I just like these round numbers. Uh, you know, so that I'm just going to say 100 volts RMS, and my breaker, assuming it tripped at its rated value of 100 amps, okay, then my question is, all right, so if I was getting 100 volts and 100 amps into my house, okay, I guess the first question is, what is the resistance of my house? Okay, so you know, coming into my house, the everything in my house, if you add all that up, my electric range, my electric water heater, and all the different things in the house, and we add these up, so then the question becomes, what is the resistance? Well, we know by Ohm's law, and I am recording now, right? Double check. Okay. All right. So, but we know by Ohm's law that the resistance, okay, is the voltage divided by the current. All right. And so we have 100 volts divided by 100 amps. And of course, that gives me a nice value of 1 ohm. So the resistance in my house was effectively 1 ohm, or actually, you know, maybe a little bit more than that if it was 120 volts, right? Then it would be like 1.2 ohms, okay? But so that's the resistance of my house when I tripped that breaker. Okay? All right, and so the other thing to think about though is what is the power? Okay, so if we you know, the power is the voltage times the current, right? So that's 100 volts times 100 amps. Right? And so that gives me 10,000 watts, right? Or 10.0 kilowatts, if we're going to put that in Blackboard. Okay, running off the edge here of my board. Okay. Apparently, I've got to change a setting on this board. It's uh, not acting like I'm used to it because, like I say, I totally lost my system. Um, anyhow, so the question now becomes, if that's the case, how much power did the electric company have to generate to get me 10 kilowatts at my house? Okay. I mean, obviously they had to generate 10 kilowatts, right? But, you know, if you look here, we've got this wire, and just again, to make, you know, to make life easy, I just chose it to be 100 miles. Okay. And so what we want to do here is try to determine, well, what is the resistance in this wire? Okay. And so given, you know, we just talked about the equation up here, all right? So given that the resistance is due to the physics of the wire, okay? And so this is my resistance here, but let's talk about the type of wire that we use in the for transmission. Okay, so when you're talking about transmitting this electricity from the power generation plant down to the people that are using it, okay, when you look at those wires, you see that they're actually, right, a silver color, and that's because they're actually made out of aluminum, not copper. Okay. And so actually the way they build these transmission lines is they use what's referred to as ALSR, or aluminum conductor steel reinforced. Okay. And so if you look at this here, you can see in the inside here how it's maybe just slightly darker. That is the still. Okay. So the still is in the center, and then they put aluminum on the outer edge. Okay. And still is just there for strength. Okay. So if you remember from DC circuits, we know that, like silver and gold and copper were kind of like the best conductors you could possibly get. And after that, there was aluminum. Whoops. Okay, so aluminum here. What did I do with my window? Okay, so aluminum, copper, I already said. Okay, copper had a resistivity. Okay, so the resistivity of copper was something like 10.37. The resistivity of aluminum is something like 17. All right. I don't remember the exact values, but it's going on almost twice as much resistance in a piece of aluminum wire of the same diameter that you would have in a piece of copper wire. So why do we use aluminum? Well, aluminum is much cheaper. It's much more abundant. It's actually the most abundant metal on the planet. So it's readily available, which means that it's cheaper. That's part of the reason. Another part of the reason is, it actually, I think, holds up a little bit better when you consider that you're actually um, connecting it on these big towers for hundreds and hundreds of miles. Okay. And so we use aluminum for transmission, even though it has actually almost twice as much resistance as copper does. But we do have to put this resistance, or this still inside to help strengthen it, because aluminum by itself is not strong enough to be, hook up a wire hundreds of miles long to and have it out there with the wind and the cold and the heat and all that. So we have to have this steel in there also. And the resistance of steel is even worse, is even higher than the resistance of aluminum. Okay. So here's a chart that I found on the internet, and this chart here shows you the kind of some different information about aluminum steel reinforced conductors. And so you see here, I don't know, they give these they gave them code names. So you have like turkey and swan and sparrow and robin and raven. All right, and this is the size in American wire gauge size. Okay, and so 6 is actually the smallest on the list here, and 1/0 is actually the largest. So if you look over here, I kind of highlighted the resistances for you. You see that 6 has a smaller um, area, diameter, and so the turkey here, so it has a higher resistance than the raven, which is 1/0. So with the American wire gauge sizing, the smaller the number, the bigger the wire is. Okay. And the other thing that you notice over here, though, is you'll notice at DC, okay, DC resistance is smaller than AC resistance. And part of the reason for that is there's something called the skin effect. I think we've mentioned it earlier in the semester. There's this thing called skin effect, where when you're with alternating currents, as the current is alternating back and forth, it tends to want to move on the outside of the cable rather than through the entire cable. So it tends to, the current, those electrons moving through this wire actually tend to move on the outer edges of the wire more than the center of the wire. And actually in this case that works for us, because in the center of this wire we've got steel, which has even more resistance than the aluminum portion of the wire. Okay, so but when we look at the AC, we see the what they're giving us. They're kind of simplifying the calculation. They're I mean, if you calculated the area of this, and then you would come up with this. But what they're just doing is they kind of did this resistance calculation for us here. You know, the row times length divided by the area. They kind of did the uh, some of that calculation for us. And so what they're giving us is the resistance in ohms for every 1,000 feet. Okay, so they're giving us the resistance in ohms for every 1,000 feet. And for AC, okay, and they're not actually telling us what frequency that is, but you know, this is transmission line. So here in the United States, it's 60 hertz is the frequency. If you actually increased your frequency, that skin effect has more effect, and the resistance would actually go up more. But they're giving us here AC 75 degrees Celsius, okay, which is actually really hot, right? Because this is Celsius. So if you notice, they gave us DC was about 20 degrees Celsius. And so if you remember, Celsius is to calculate between Celsius and Fahrenheit, you basically multiply by 9/5, which is almost 2. So you basically double that would give you 40 degrees, plus you add 32. So, you know, so 20 degrees Celsius is kind of right around room temperature, where 75 degrees Celsius is much hotter. Okay. But you also got to remember that as current is flowing through this, it's heating it up. Okay, so on a very hot day in the summertime when it's 90 or 100 degrees out, you got the sun beating down on it, and you've got lots and lots of current running through it. It's going to be way, way hotter than, you know, room temperature. Okay, so you got to keep that in mind too. So what we're going to do is we're going to use this setting here of 0.806 ohms for every 1,000 feet. Okay, so that is our value of resistance for this wire. Now we're going to ignore we're just going to say it's 100 miles from the power generation plant into my house. Okay, so let's just calculate the resistance then. What is the resistance? Now remember, the resistance inside my house was 1 ohm. But now I'm asking, what is the resistance to my house? Okay, which is running through copper wires, right? It's not running through my electric stove or my water heater or my laser printer or my TV or anything like that. So let's take a look here, right? So we'll calculate this resistance. Okay, so the resistance of these wires is 0.806 ohms per 1,000 feet. Okay, but I've got miles. Okay, so then we have to convert. So we got to take 5,080 feet per mile. and then times 100 miles. Okay. And so miles will cancel, feet will cancel, and I will be left with ohms. So if we calculate that, right, so come over here to my handy dandy octave calculator, right? So we have the resistance of the wire to my house here is, resize it so I can see the equation, right? So it's 0.806 times 5,280 times 100 miles divided by 1,000 feet. Okay, so, oh wow, look at that. 425. Okay, so 425.57. So the resistance of the wire is 425.57 ohms. Okay, so to get to my house, we've got to push this electricity through a resistor of 425 ohms to get to that 1 ohm of resistance in my house. Okay, so I don't know what you guys think about that, but that's kind of crazy. Okay, here I am at my house and I have 1 ohm of resistance, and yet the electric company has to push all that electricity through over 400 ohms of resistance just to get it to my house every day. Right? So if that's the case, then the question is, what is the voltage, right? Remember, it's the voltage that pushes the current. Okay, so the voltage pushes the current. So let's take a look here, right? So we have a little AC circuit here, and I have a resistance here, and I have the resistance here of my house. So this is the resistance of my house, which is 1 ohm. And this is the resistance of the wire, which is 425.57 ohms. Right? And we know right here we have 100 volts, and the current flowing through is 100 amps. So the question is, what is the voltage over here? It's a series circuit, right? So it's 100 amps, right? So the current is still 100 amps, but the question is, what is the voltage that they're supplying me? Okay. So, this is really a simple voltage divider type of circuit here, or if you wanted, we could, we could just come up with like simplify the circuit there and say that, the kind of the simplified circuit has this resistance of 425.57 plus this resistance of 1 ohm. So we got a total resistance of 426.57 ohms. And so the power is, or the voltage at the power company, right? So the voltage the power company is supplying me is going to be, you know, knowing that I've got 100 amps flowing through here, right? So they're going to have to be supplying 42,000, say 657 volts. Okay, so these guys over here got to be generating 4,000 or 42,657 volts, right? Or, you know, 42.7 kilovolts if we were to like maybe put that into Blackboard. So what do you guys think about that? That's kind of crazy, isn't it? Uh, I believe the resistance was just 426 ohms, Austin, not 426,000. Because we got to divide by the 1,000 over here, right? Okay. Does anybody else verify that I calculated that? 425.57. Okay. All right. So what do you guys think about this, right? That's just crazy. We're I've got 100 volts in my house, and the electric company has to generate 42,000 volts to get me that. So let's look at the power, okay? So what is the power that they got to generate then? Okay. So remember, power is V times I. So that's 42.7 kilovolts times 100 amps. Okay. So we got to shift this two more decimal places, right? So 42,000. I want to make sure I'm doing it right here. Um, so that's going to give me 4270 kilowatts, right? Or 4.27 megawatts. Okay. So for them to give me 10,000 measly watts over here, they're going to have to generate over 4 million watts. Okay. You know, that's just crazy, right? You can't, how can they make any money, right? Because well, what are they going to do? They're going to be charging me for 4 million watts, and they're only giving me 10,000 watts. That is ridiculous. That's crazy. Something's going on here. All right. So let's take a look at a transformer problem then. Okay. So if we come down here, okay. So now, uh, by the way, if you grab the slides from last night, I noticed there was a typo here. This transformer is a 100 to 1 transformer, not 100 to 1. All right. Okay, so now we can't do anything about this resistance, right? The resistance of this wire, there it is, sorry. Okay, the resistance of this wire is 425 ohms of resistance. Okay, I mean, that's the wire. We can't do anything about that. Okay, that's how much resistance is in the wire. And you know, that's non-negotiable. You know, that's the resistance of the wire. If you want to transmit that wire, that power through this wire, you've got to have this resistance. Okay, that's it. Okay, that we just got to live with that. However, if we use a transformer, okay, if we use a transformer, what's going to happen here is we can step up the voltage. So instead of them providing us at my house, outside my house here at my transformer, instead of them, you know, they're at, you know, inside my house, they're still giving me 100 volts. But we go out to the telephone pole, or the electric pole, really. I don't know why we still call them, I still call it telephone poles, right? But there's a transformer out there. So what we're going to do is we're going to use a transformer that's going to step up the voltage so that or step down. Technically, it's stepping down the voltage. So what's going to happen, it's a 100-to-1 transformer. So I've got 100 volts on my side of the house, but on the other side of that transformer, it's the voltage is 10,000 volts. Now, the way transformers work, what's so critical about transformers is they give you, if it was a perfect transformer, then the power into the transformer is equal to the power out. Okay. So the power in is equal to the power out. But remember that power is voltage times current. Okay. And so therefore, if you know, my power out over here is 100 volts times 100 amps, okay? So if I step up my voltage on this side to 10,000 volts, then I need only 1 amp to get 10,000 watts. So over here I have 100 volts. I have 100 volts times 100 amps. But on this side, I have 10,000 volts times 1 amp. Okay. For the same power, okay, so if it, again, it has to be, we're talking an ideal transformer here. Okay. So we got 10,000 volts. If we use this transformer, I can step up this voltage to 10,000 volts. So what that means is that when I'm going through this resistance here, it's, instead of it dropping 42,000 volts, it's going to drop, it's only got 1 amp, right? So my resistance is 425.57 ohms. We just round that up to 426 to 3 significant digits, right? So 426 ohms with 1 amp flowing through it. So it's going to drop 426 volts. Okay, so 426 volts is going to be dropped across this wire. However, so that means on this side of the transformer at the electric company, they have to supply me. Now remember, they're supplying outside my house into that transformer, and my side of the house, they are supplying me with 10,000 volts, okay, on the high side of the transformer, okay? But what do they have to supply on their end? 10,426 volts and 1 amp. And so that means then when you go over to the other side of the transformer, so when you go over to the other side of the transformer, they have to generate 104.26 volts, which means that the power that they're generating, okay, now they, whoops, whoa, that really went wild. I gotta make sure I don't touch this pad there till, all right, so the power, they're still, on this side of the transformer, I still need 100 amps. So I have 100 amps on this side with 104.26 volts. So the power over here is 10,426 watts, right? Or 10.4 kilowatts. All right. So over here, right, I'm using 10,000 kilowatts. Okay. So I'm going to pay, basically they're going to be charging me to pay for 10,000.4 kilowatts. Okay. So yeah, hopefully you can see the beauty of these transformers. Okay. So instead of me having to pay the electric company and the electric company having to generate 4 million watts, all right, instead of me having to pay for 4 million watts when I'm only using 10,000, okay, the electric company is going to generate 10,400 watts. Okay. And that 400 watts is because they're going to lose that in this resistance. Okay. So because I've got to, basically I'm paying for them to not only generate me my 10,000 kilowatts, or excuse me, my 10,000 watts or 10 kilowatts, but I also have to pay for them to get it to me, right? So that's part of it, is that delivery charge, right? But they're only generating 10.4. Okay. So I got to pay for them to transmit it, which is 400 watts worth. And so you can see, without transformers, without the ability to change that voltage, the electric company couldn't make power plants big enough to supply. I'm just talking about my house with a 100 amp usage, right? What about all the other houses and all the companies? Okay. So so these transformers just make it possible for the electric company to actually be able to do something. All right. And the key points there is because the electric company, or not the electric company, but transformers, basically what they do is, we have whatever power we're putting in, that's what we're getting out. Now, that's not quite true. There are going to be losses in the transformer. All right. But they're fairly efficient. And you can see by being able to step up that voltage, because remember that the key here is that your loss, right? The power in the wire is equal to I squared times R, right? That's the power in this resistance, right? There's this resistance in this wire. Okay, so the power being lost is I squared R. So if I is equal to 1 squared, right, times, 1 squared is just 1 times the 426 ohms at 3 significant digits gives me, I'm losing 426 watts. Okay, so the wire is using 426 watts, where up above it was using 4 million watts, because if you have 100 amps, right, you have 100 amps squared times 426, right, so that gives you this 4.26 megawatts. Okay, so, and this is just all loss. This is loss. This is wasted energy. Okay, but if we can step up the voltage, we can then, it steps down the current. And so that's how we can actually transmit this energy. All right, so let's go ahead then and go through some of these slides here and just kind of walk through this. So there's a couple of different types of transformers. Number one, there's something called the isolation transformer. And for the most part, 90% of the transformers that are made are isolation transformers. So not only does that transformer outside your house uh, step up and step down the voltage, but it also provides isolation, electrical isolation between you and the power company. Okay. The other, another type is called auto transformer. An auto transformer only has a single winding. Okay. And then there's instrumentation transformers, which allow you to step up or step down the voltage to get accurate measurements. And because like you can't walk outside with a voltmeter and measure the voltage on the high side of your transformer. If you did that, you would get electrocuted, right? 10,000 volts is not a good thing to be, trying to get up there and measure with your multimeter. Okay, it's very dangerous to do that. So they have these instrumentation transformers where you can step down the voltage to a safe value and still get very accurate measurements. All right, so as the purpose that I already hopefully kind of gave you a good demonstration of at least one purpose of the transformer, is that it steps up or steps down that voltage. Another purpose is that you can actually have taps on the transformer to get multiple voltages. So one of the things that they do in your house is actually, right, you don't get 120 volts, you get 240 volts, but then they put in a center tap. So you actually get two circuits in your house of 120 volts. So when you're running your TV and your computer and things like that, you're running that off of 120 volts. But when you're talking about your electric water heater or your electric range or your electric dryer, that was the other thing I didn't mention, your electric dryer. So I've got, because I don't have gas in my house. Some of you may have gas in your house, so you don't use near much electricity. Okay. But, if you have electric range, electric dryer, and electric water heater, those are really big loads. And so the same thing, instead of running those at a lower voltage of 120 volts, those run at 240, which means you reduce the amount of current you need to power those. Okay, because they use twice the voltage, so they only use half the current. Okay. All right. So, when you look at transmission lines here, um, you see that you see these great big wires here. So you see here, I don't know if I can zoom in on this anymore or whatever, but you see there's actually on these ones, there's 4 wires, and I've seen some that have like 6 wires or whatever. But actually, you know, those, those are all one circuit. So we see here, there's actually 1, 2, 3 circuits there. Let me give it a little pointer here so you guys can see what I'm kind of referring to. So you see right here is one circuit, and then this is a second circuit, and then there's a third one here. So they're transmitting in three wires there, and we're going to talk about that next week as 3-phase. Okay, so that's 3-phase there. But these are very, very high voltage lines here. These are probably, these aren't 10,000 volts like the example I just did. They're more like 500,000 volts. Okay, so they're very extreme high voltage here. So where on the other hand, if you look at your house, okay, this is a transformer that you might see at your house, and you see here, see how big this can make. I had a picture of, actually, I took a picture of the one outside my house so I could zoom in, but I'm not quite sure where that picture is at. But you see here, there's 1, 2, 3. This is that center tap into your thing. So right here is the wire coming down, and there's a fuse here to protect the transformer, that it'll blow a fuse. And then you see here's the high voltage connection over here. So there's a very large isolation connection here, because you got the high voltage 10,000 volts or whatever the voltage. It might only be about 7,000 volts, but it's still a very high voltage out here in the thousands of volts here coming in. And then it steps down and runs to your house. Now what's running to your house is only 240 volts, separated it by this. So you've got this center tap, and then you got 120 volts to the center, and then you got 120 volts on the other side. So if you go across the whole thing, that's 240 volts. All right. So, but as I say, that the key to this working is this concept of power in is equal to power out. So if we can increase our voltage by 100 volts, by going through a step up of 100 to 1, then we reduce our current and get the exact same power. Okay. Another thing to keep in mind is the analogy of a transformer. If you think in the mechanical thing, you get the same thing out of gears. If you think about like the transmission in your car or something along that line mechanically, the transformer is analogous to a gearbox in a mechanical application. All right. And so the way that works, right, is when we talk about an inductor, okay, these are just what we were talking about there, but when we talk about an inductor, okay, an inductor is a coil of wire, and that generates what we refer to as um, self-inductance, okay, and it generates that magnetic field. So what we do with the transformers, we take two coils of wire. So we take two coils of wire and we connect them together. We connect them together through the same magnetic core. Okay, so we have this magnetic core, but we have two separate coils of wire now. So we have one side we refer to as the primary side, which is where we're going to hook up the voltage source. And then the secondary side is going to be our load side that we're going to connect up to our load. All right. And so we have a different number of windings here. Okay. So if we have 100 windings on the left side for every single winding on the secondary side, that gives us a turns ratio of 100 to 1. And so this is going to give us a voltage. Okay. So the step up gives us the voltage here. Don't know why they always. So the voltage here okay, so the voltage is, this is the high voltage, okay? And so this is the voltage on the primary side, and it's, so let's say it's 10,000 volts over here. So when we take it over to the other side, then through this winding, the voltage steps down. So we get 100 volts. Okay. So this would be a step down transformer. Okay. So we've got 100 windings on the primary side, and for every one winding on the secondary side. So we're stepping down the voltage. However, when you step down the voltage, you actually step up the current. Okay, but when we talk about whether it's a step down or step down, we're talking about what the voltage. Is it increasing or decreasing the voltage? Okay, so this would be like a step down here. All right, so we've got this, again, it's this way, what we refer to as the mutual inductance. So the mutual inductance is this magnetic energy stored inside the core of that, but since they're sharing the core, they're sharing that inductance. Okay, so instead of getting a phase angle, so this is something I want to make a point of. I don't know if I say it in the slides here, so I'll write it down here. Okay, mutual inductance does not shift the phase. Okay, so there's no phase shift in a perfect transformer. Okay. So whatever the phase angle of the voltage is, it's the exact same phase angle here. Okay. So another thing to make note of here is they use something called the dot notation. Okay, so what they do is they put a dot on the transformer on the primary and on the secondary side. And what that dot does is tell you which, whether it's like a plus or a minus. It's supposed to look like a plus here. Okay, and let me change the color of this. All right, so if it's a positive voltage here at this dot, then the dot shows where the positive voltage is going to be at the secondary side. Okay, so with this example here, the dot, we have like the current is flowing into the dot, the current is flowing out of the dot. So notice here you see the arrow, it says the secondary current is coming in here. Okay, so that's what they refer to as the dot notation. All right, something else we have to be concerned of is when you first hook up the electricity to the transformer, you get this inrush current. And so you get these like high spikes of current due to the magnetizing of it. So, you know, the transformer was sitting there, it had no current flowing through it. So if there's no current flowing through it, the core is not magnetized. And so when you first hook it up, you have to actually get that energy into the coil, and so you get these like spikes of large current, which is energizing that coil. Now after that, remember what happens is you're actually only energizing that, you're only energizing it during part of the cycle, and during the second half of the cycle you're dumping the energy back out. And so that's why the current is reducing, is because it's getting that energy, you know, so you first have to get some energy in the coil. But then as you start building it up, the spikes of current drop because it starts dumping that energy in the other half of the cycle, so it's passing that energy back and forth. Okay, and so you know, so you get to this point at where the circuit gets basically equalized, and so you don't have these huge spikes. But when you first hook it up, you can get these very high spikes of current, which is referred to as the Inrush current. All right, transformers only work for AC voltages. Okay, they don't work for DC voltages. And they are highly efficient, but they do have some losses. Okay. All right, this is just showing the magnetic lines of flux. Now, sometimes these lines of flux, right? These lines of flux is the flux going through the two coils. So if you look at this lower example here, okay, so here you have two coils. You have your primary coil and your secondary coil. And what it's showing here is it's showing the flux go through the secondary coil, but it's also showing some flux that's not going through that coil. So this flux over here that's not going through the secondary coil is referred to as leakage flux. Okay, and so the book talks about a couple of different terms. One of them being the coefficient of conductance there. Let's see. I forget one of the terms they refer to as leakage inductance. Okay, so they talk about leakage inductance. Leakage inductance is that inductance that, or that flux that is not leakage flux, sorry, is the leakage flux is the flux that's not flowing through the secondary winding. Okay, so and then they have the coefficient of coupling is the term that they use. The coefficient of coupling is referring to how much of this is actually, how much of this flux is being coupled and therefore passed into the secondary winding. All right, so that now the reason that it only works with AC is because we're passing that energy through this magnetic core by we're creating this magnetic flux, and then we're flipping it over and we're taking it back out and generating it in the other way. And it's this change in the magnetic energy within that core that is then passed on to the second coil. Okay, so you've got to keep the magnetic flux changing. If it doesn't change, if you remember, like in DC, if we pass a D current through a inductor, then what happens is we just energize that core, and then it just looks like a short circuit. Okay, so we've got to keep that magnetic flux changing to use this transformer. All right, so the step up and step down, as I kind of mentioned before, right? We have these. If you have more windings on the secondary side, you're going to step up the voltage. So that's what, when we looked at the example for the power company, they're actually generating it at a fairly low voltage. So when they generate the electricity at the power company, they're generating the electricity at maybe 480 volts, or maybe 1,000 volts or something like that. They're generating it, but then they step it up to 100,000 volts or even 500,000 volts to send it, to transmit it across those miles and miles of wire to get to your house. And so they actually, that's why sometimes you'll be driving down the road and you'll see a substation. What the substations do is they break it, they drop it down to a lower voltage, right? So that those lines outside your house, those transmission lines outside your house, they're only running at maybe 7,000, 10,000 volts. But those great big transmission lines are carrying voltages way up at, some of them are like 500,000 volts. And so, so they have these substations that break it down from the really, really, really high voltages down into just high voltages that are run out then to the local communities. All right, so now a lot of times they'll have like center taps and things on the transformers. And so you can see here there's a couple of different drawings here of these transformers, and they're kind of showing you different connections. So you can, if you run through all the windings of this transformer on the secondary side, you're going to get 240 volts. But if you just go between, so if you run through all these windings you're going to get 240 volts. But if you're running through, um, the local, or just the half of it, then you get 120 volts here, and then here I've got a second circuit which is also 120 volts. Now notice the ground here. All right, so they've got this connected to ground here. There's no ground connection. I mean, there is a ground connection over here on this side, but it's a completely separate ground. So that's that isolation I was talking about. All right, so not only do we have this change in voltage from the high side, which is 12,000 volts is what this one's showing over here, and only 240 volts here. So not only do we have the change in voltage and the change in current, but we also have an electrical isolation. Okay. All right. So, and then we have like these phase markings, or these dots that indicate the the if you have like a positive here, that's giving you a positive, then if your voltage is positive, when it's high, a positive, then the phase mark is going to be where the high side, on there, on the secondary side. All right, so I don't know. Let me try to blow this picture up here, just give you a better view. All right, so when you look at your use a red color here. All right, so when you look here, you see coming to your house, a lot of, if you live in a lot of these communities, they actually bury these wires now, so you don't have to see them. But you can see up here that the up here is the very, very high voltage. And then there's a second wire here, which is the ground wire running back, right? Because for them to provide you electricity, they have to have two wires, right? So they're providing you wire, and it's coming in here. You got to have current flow, so you've got to have a complete circuit. Okay, so here's this one wire coming in, and then there's the ground wire. So notice this one's a high voltage, maybe 10,000 volts, and that's why it's so far away. Where this one here is effectively 0 volts, it's ground. Okay, it may not actually be 0 volts compared to what your house is and inside your house, because it's a separate ground. Okay, so this ground wire is separate than the ground in your house. And so therefore it actually may, compared to the ground at your house, may be 10 volts or even 100 volts or something. All right, we don't really know what that voltage is if we tried to compare it to there, but it's certainly no 10,000 volts. Okay, and so we have this high voltage here, and so you've got that isolation, but then this wire here is really close to the transformer. But then you see, and it doesn't show very well in this drawing, but they run this wire down here, and here's your insulator. So you got this great big ceramic insulator here that this wire is running to. So if you go out and you look at a house that's got the electric coming, on overhead lines like this, you'll see that there's going to be a wire running over there, and there's a fuse there, and then it's running into this large insulator and coming in, and then you see that the ones running to your house are just coming right out of there. They don't have that great big ceramic isolator because they're not at 10,000 volts. They're only 240 volts. Okay. All right, so what we have is a turns ratio. Okay, the turns ratio, you have the turns on your primary side versus your secondary side. Okay, and so I'm not sure what this slide here is. They've got them flipped on this slide for some reason. I just noticed that. I don't know why they're flipped here, but so your turns ratio, a lot of times they just use like the letter A or A to 1, and it's a lowercase a, and that's your turns ratio. And so it's actually I don't look at that other slide. I don't know why it's reversed like that. They got it kind of flipped there, but it's your turns on your primary side to the turns on your secondary side. All right. So if you, for instance, have 240 turns on your primary side and 60 on your secondary side, then your turns ratio is 4 to 1. Okay. Just to warn you, in the homework, you got to watch one of the homework problems. I give you like a turns ratio of 2 to 1 or 4 to 1 or 10 to 1. I don't remember what it was, but it's just a ratio of this. The other one I give you, you got to actually do the calculation. Okay, so don't let that trip you up or you get some wrong answers there. Okay. All right. So again, what happens is when you look at the voltage, okay, the voltage on the primary side. So to calculate the voltage, you have your voltage on the primary side. Let's say it was 10,000 volts. Okay. And then, so to get the voltage on the secondary side, right, you take and you divide by A. So you divide V primary by A. So if A was 100, which is the example I did earlier, right? So you have 10,000 divided by 100. So your voltage dropped down by 100, but your current goes up. So the current on the secondary side is equal to A times the current of the primary side. Okay. So remember the key again, this is really the key here is the fact that power, which is volts times that, is the same. So power in is equal to power out. Okay. So it doesn't matter what the turns ratio is, okay, in an ideal transformer, okay, you put in whatever power you put in, that's what power you're getting out. Okay, so isolation transformers, you can buy an isolation transformer that's got a turns ratio of 1 to 1. And if you do that, the whole purpose of it is to do nothing but isolation. But most of the time, you get both a step up, step down, and isolation at the same time. Most transformers are isolating. Okay, so here's kind of a picture of you showing you, right, here's your two windings to your power on the primary side, and here's your load connected to the secondary side, and there's no electric wire connection between the two windings in this drawing here. Okay, so you've got your primary winding, you got your secondary winding, and the only connection is through the magnetic core. Okay, So that gives you perfect isolation electrically, and that's very convenient. That way, if the electric company, if you think of those transmission lines, them hundreds and hundreds or even thousands of miles of transmission lines going across the United States and into Canada. We actually get electricity here in Ohio. We get some electricity from northern Canada, and they have large hydroelectric dams way far north in Canada. I think I may have shown you that in class before. And that is transmitted thousands of miles down to us and down here into New York and Buffalo and Pittsburgh and Cleveland. And, so we might be getting some of that electricity. So you think about thousands of miles of that, lightning's going to hit those sometimes. But we get isolation from that electrical isolation because of all the transformers that it's got to go through. Okay, so we do see spikes in the voltages due to the lightning hitting it, but we don't have a direct electrical connection. Okay, so this is a picture of isolation transformer here. So there's no connection between the high side or the primary side and the secondary side. Okay, and it's also showing you the turns ratio calculation there. All right, and this is just showing some different windings. Some of the different transformers, you can actually hook them up a couple of different ways. So like in this case here, we have this, we got 4 windings. All 4 windings share the same core. We have 2 primary windings and 2 secondary windings. So if we hook it up with the 2 primary windings in parallel, all right, so this is in parallel. So we got the high side H1 and H3 are connected together. And the high side H2 and the low side of this winding H2 and the low side of this winding are connected together. So that is giving me like two coils connected in parallel. And so that gives me double the current, but a smaller voltage. And so I'm just kind of trying to show you all the different connections here. On the other hand, I could have like 12 volts. I have 12 volts here, and then this is connected. This is one node here, and then I have another 12 volts. So I could put 24 volts across here. Okay, so I don't have quite as much current, but it's actually the same amount of current through each coil. Okay. So these are just some different connections here. An auto transformer is one that we have one winding with like a tap on it or multiple taps. Okay, and so this is a little bit simpler to build, but it doesn't have any isolation. Other than that, it works pretty much identical to the isolation transformers, but it doesn't have electrical isolation. If you don't need electrical isolation, this might be a little bit cheaper way to go. And sometimes it's nice to share a ground between your primary side and your secondary side. And, so, if it's okay to share the ground, then an auto transformer will work for you. Okay. So a lot of times we have these little control transformers or whatever. I mean, you'll see these inside of your power supplies. If you were to, open up like the power supply inside of your PC, if you have like a desktop PC or something like that, you'll see these. Typically these are going to be isolation type transformers. and just showing some different connections. Sometimes some of these control transformers will have the primary side will have the double windings here, so you can either hook it up to 12 volts or like 120 volts or 240 volts or whatever, and then step down to the secondary side. And this is just a chart showing some of the different values here. Okay. This is just pictures showing the instrumentation transformer. Okay. I know I'm going through these slides here so you can look at these. Now here's an example of an instrumentation transformer, specifically a current transformer. And the beauty of these is the fact that you have a large current flowing through uh, a conductor. All right, like say it's feeding like a very large motor, and you can't. Number one, most ammeters and things only read milliamps or maybe up to 5 amps. Okay, so if you had a motor that was requiring 100 amps through it, okay, you wouldn't want to put that through a meter because, for one thing, that meter, if you connected it in series like we did in class, it may have 10 ohms of resistance in it, which, for what we did in class running milliamps through it, it was no big deal. But if you think about it, we already did this. 100 amps flowing through 10 ohms means it's going to be dropping 1,000 volts. You can't be losing 1,000 volts on your ammeter just to try to detect the current. So these things are beautiful because you just actually clamp them around the outside, and they pick up that voltage, or they pick up the magnetic flux from the current flowing through them, and then you induce that, and then you can measure the current without actually ever breaking that and throwing in an extra resistance in there. So it's just very convenient. So in this case, the primary side only has one winding basically. Okay, so there's like one winding. It's not even a complete winding. It's just that wire running through there, but it's such a huge current. It's generating that magnetic flux, and we're able there then to run that into our thing. And remember that you have more windings here on the secondary side, which means that you have a higher voltage, but you have a lower current. So so you have 100 amps over here, you may only have, say 10 milliamps flowing through the secondary winding, right? So all right, so these potential transformers here are kind of doing the same thing. They're using it to convert a very high voltage down to a lower voltage, just so we can measure the voltage and monitor what the voltage is. Okay. All right, now some other transformers we use to get a very high current for a short time. Okay, so one place we see these are with the older style fluorescent lighting. Okay, and so we've got to actually get very high, um, very high voltages, and then we basically discharge that voltage through there. One place we see this is with bug zappers. I remember, actually, I was kind of a kid when bug zappers first came out, and I remember this guy telling me, "Hey, this thing's got 10,000 volts in it." I'm like, "There ain't no way you can have 10,000 volts." Well, with a transformer, you can. Even though you're only putting 120 volts in it, on the other side, you're getting 10,000 volts, right? But the current is very small. Okay. So, so those are some various uses here where we see these, we don't think about it. All right. Transformers are given in volt amps. So remember we talked about power, real power, we talked about apparent power, and we talked about reactive power. So apparent power is rated in volt amps. Okay, and so transformers, they have a nameplate rating on them that give you the power, and it'll be in VA, and that rating is on the load side. Okay, so in reality, we say that we like to say that transformers are ideal, but they're not, right? They're inductors. They have lots of wire in them, and so there's a lot of resistance. They also have that leakage flux that we referred to, and they have those eddy currents in them that we also talked about with inductors. And so they transformers, some of them maybe only give you about 75% efficiency. Okay, so 75% is actually kind of a bad transformer, but they do have this, they're not perfect. They do have losses in them. Okay, so they have copper losses due to the current and the coil or in the wire. Now remember, you've got current on the primary side and current in the secondary side. Okay, and remember that let's say that you're going to step the voltage up. So you have 100 volts coming in, you're going to step it up to 10,000 volts. Okay, and so your current is going to step down. So if you're doing a step up, the primary side windings, actually the size of the wire on the primary side is going to be much bigger wire because it's going to have a lot more current. All right, it's going to have 100 times more current on the primary side because your voltage is lower, but then you're stepping up. So the voltage is going up, but the current then is going to drop. So if, one side of your windings are going to have a very wide uh, current in it, or a very wide diameter current, and the other side will have a low. Okay, so Andrew, you're asking, is the lower current due to the fact that the more winding? No, the lower current is due to the fact that power in is equal to power out. And so the voltage went up, the current goes down. Okay, the resistance in the winding is due to the loss, or is a loss, meaning that power out is not actually equal to power in. So in reality, power in is equal to the power out plus the power lost. Okay, so in reality, this is the true equation of a transformer. You have however much power you're putting in. Okay, well, you're getting that out to your load, but you're also losing it. Where are we losing it? We're losing it in the resistance of the wires, both on the primary and the secondary side. And we're also losing it due to the eddy currents in the core. And that's basically causing that leakage flux. Okay. All right. So one way to reduce the eddy currents is to use multiple thin plates of metal for your core. So when you look at most transformers, you see instead of them just having one solid core of iron, they have lots of these little plates in there. And the reason that they do that is because it minimizes the eddy currents, because these things are isolated. They have a little coating of insulation on them, so they're isolating the eddy currents, so you can't just have lots of current flowing through it. You have little eddy currents through each one of these, but it reduces the amount of current. Okay, so I say a lot of transformers are considered 90, somewhere between 90 to 99% efficient. Okay, so like that other slide had like 75%. If you have 75%, that's not very efficient. All right. Another thing that you see sometimes is they have multiple taps on the transformers. And the reason for this is because as you change your load, as your load changes, the amount of current flowing through it is going to increase as your load increases. And so therefore you're going to have a voltage drop. And so some of these fancier transformers, you can actually tap off of them at different places, and that'll give you a slightly different voltages. All right, so we're going to talk about the three-phase next week, so I'm kind of flip through that. All right, so I say the core thing is right here. Okay, with an ideal transformer, power in is equal to power out. And so whatever the voltage in is, okay, so if you have a transformer that is stepping up 100 to stepping up, so it'd be 1 to 100, then your voltage in, say, is 100 volts. Your voltage out then becomes 10,000 volts. Okay. Not fitting on the screen here. All right, so your voltage out would be 10,000 volts, but the current then, all right, so the current in 100 amps becomes 1 amp. Okay, so you step up the voltage from 100 volts to 10,000 volts, but you step down the current, because power is the voltage times the current. Right, so on the left-hand side, I've got 100 times 100, which gives me 10,000. And on the right-hand side, yeah, it should be watts. So you put 10,000 watts is equal to 10,000 watts. Okay. Okay. So that is the key. This whole concept of power in is equal to power out. Okay. Which it's not quite perfect, but it definitely makes it so that we can that we can have electricity in our homes, right? Because without this, right, if we go back and look at my original example, here was the original example. This is the copy in the slides, right? And again, my turns ratio is wrong here. So the turns ratio is 100 to 1, not 10 to 1. Okay. But, all right, the power company would have to generate what do we ended up saying? It was like something like what, 4.2 million watts. 4.2 megawatts to give me 10,000. All right, so they would have to be over here generating 4.27 to get me 10,000 watts at my house. But with a transformer, with simply a 100-to-1 transformer, all right, they were able to generate 10,000 point, 10.4 kilowatts to get me my 10. All right, so here they only have to generate 10,000.4 kilowatts to get me my 10,000 in my house. Okay, so like I say, I just hopefully this gives you a good demonstration of why these transformers are so important. And when you're driving down the road and you see these power lines and you see the transformers or the substations and stuff, you can understand purpose and how important they are. And really, when we talk about electricity, right, the one huge aspect of it is power generation and transmission and distribution. Okay, and nowadays with the various different solar cells and windmills and things like that, we're going more to a distributed power generation kind of thing, but we use so much electricity. Even for those of you, Josh, who do have natural gas, right? That natural gas furnace you've got or a natural gas dryer you've got, still not going to work without electricity. Okay, yeah, it doesn't use nearly as much as my electric dryer, but it's not going to work. Okay. So, I mean, it'll, you can say, well, okay, it can heat up, but it's not, it's not going to blow the air through your house without that electric fan attached. So electricity is, we've really come to a society now that we can't really live without it, right? It would, you can't even start your car or your truck without it, right? You need that electric starter and that battery in there to start it. And if it's a gasoline engine, to get that spark, that's electricity, right? So yeah, let me just kind of talk about that for a minute here. When we talk about auto transformers, okay, so an auto transformer is basically the coil in your car. So if you think about your car, you have this 10-volt battery or 12-volt battery, technically, I guess. Okay, and there's a switch here. Nowadays they're electronic. But then you have this auto transformer. Okay, so that coil in your car is really an auto transformer. And so what happens is when this switch closes, it puts energy in this magnetic core. And then you have over here your spark plug, right? And there's that ceramic part around your spark plug, because this thing then is going to be generating, so you've got this spark gap here, and this of course then is connected to ground, and this is connected to ground. So here is the case, the car is a perfect example of a auto transformer where you need to have a common ground here. Okay, so you've got to have this common ground. And so you're going to get, I don't know what is like 10,000 volts or whatever the voltage is here. I don't know if it's quite 10,000 volts, but you get that high voltage there, which gives you that spark to ignite the gas air mixture in your internal combustion engine. All right. So if you have a gasoline engine, you need that electricity. Okay. And so this is basically how they do it. So you close the switch over here for an instant, that energizes this coil, and then you open this switch, opens back up. When the switch opens back up, it generates this huge voltage that then allows it to jump from this conductor here to ground and get a spark to ignite the engine. All right, so that's pretty much it for transformers. I guess one other aspect that maybe I need to talk about, though, is the impedance. So if we have a transformer, and I'm going to, of course, use easy numbers again. Okay, so we'll go in here. And let's just say that I have a transformer here with 100 to 1 windings here. So, and here's this dot I was talking about. I don't know, I thought the slides. So the current, so if this is positive, when it's a sine wave going in, so it's going positive and going negative. But when it's positive at the dot, that means it's positive here, and the current's going to be flowing out of the dot now. And so then, so let's say that we have a resistance over here, and let's just say that, I don't know, let's say that this is going to be 10 volts over here. Okay, and so if we have 100 to 1, then we would have 1,000 volts over here. Right, or 1.0 kilowatts or kilovolts. And so let's say that this is 10 ohms. Okay, so this is 10 ohms. So our current I on the secondary side, so I on the secondary side is going to be 10 volts divided by 10 ohms, which will be 1 amp. Okay. And our power then is going to be V times I. Okay, now notice in this case I haven't put in any inductors or capacitors, so the current is in phase with the voltage, because technically power is voltage times current times the cosine of the phase angle. But since I don't have any capacitor or inductance in this, the cosine, the angle is 0. So it's the cosine of 0, which is simply 1. Okay. And so we're going to have 10 volts times 1 amp, which is going to be 10 watts. Okay. So, right. And then if we look at our impedance, right, our impedance, which is just resistance in this case, all I have is resistance, is the voltage divided by the current, which is 10 volts divided by 1 amp, which is 10 ohms. Okay. So the question is, what does the resistance look like to the power supply? All right. So they talk about this reflection. Okay. So another thing they talk about in the book is reflection. Reflection impedance or reflected impedance. So this is kind of the definition out of the book here. Let me just paste this right in here. Okay, so this is the definition out of the book. Reflected impedance is the impedance appearing at the primary side due to the load connected on the secondary side. Okay, so I just need a little more space here. All right, so given that, then on the secondary side, remember here, this is our turns ratio. Our turns ratio here is A to 1, which is 100 to 1. Right? So on the primary side, we already said that our voltage is 1000 volts. Okay? Because let's see, 10 times 100 gave me 1000, right? But our current then, our current was 1 amp. Okay, and so we're going to, we're stepping it down, right? So it's 1 amp divided by that. So the current becomes 0.01 amps on the primary side, right? So our impedance which in this case is the resistance, is the voltage divided by the current, which is 1000 volts divided by 0.01 amps, which is 10,000 ohms, or excuse me, 100,000 ohms. Okay, and so that is A squared times the impedance of the load. All right, so the impedance of the load was 10. So we take 100 squared, because A is 100. So we take 100 squared times 10. All right, so 100 times 100 times 10. So that gives me 1, 2, 3, 4, 5 zeros. All right. So the all right. So basically, if you're just talking impedance in general, the impedance on the primary side is equal to your turns ratio squared times your impedance ratio, or times your impedance of the secondary side or the load. Okay. So that's this piece here. They're talking about reflected impedance. So to reflect it, you get this a squared term in there. So that's where that comes from. All right, so that should be sufficient enough to get you through the lab. If you look at the lab, actually, one of the things I did was I just I went through the glossary at the end of the chapter because they talked about they just gave you all the definitions of the different parts of the transformer or uh, relate things related to the transformers. And as you know, hopefully my first example really demonstrates how important transformers really are. And so you know, so there's a couple of problems on calculating, you know, the reflected impedance, calculating this voltage on both sides of the transformer, calculating the power on both transformers. Remember, the problems I gave you are assuming a perfect or an ideal transformer. So your power supplied, your power on the primary side, and your power at your load, they better be the same. Okay. All right. So any questions, comments about any of that? Okay, so there's a homework there. I'm going to have a lab for you to do on Tuesday. So, you know, I'll start lecture at 9 o'clock on Tuesday and go through the lab. And then next week, we're going to talk about three phase. And we're going to have the makeup exam, exam 3. And then the week after that is the final. And that's it. We'll be done. What did I say, Alex? Did I say Thursday or something? I meant Wednesday. I definitely meant, I said Tuesday. Okay, I definitely meant Wednesday. Yes, thank you. Yeah, so Wednesday at 9 a.m. I will be doing lecture um, to just discuss the lab and like I say, it'll be a pretty short lab, but we'll just, you know, use multi-sim to build up a little transformer circuit and do a couple measurements and much simpler than last week's lab. All right. Any other questions, comments? The third exam, yeah, the second part of next Monday, I'll do three phase, and then Wednesday we really won't have a class. I'll just have the exam in Blackboard, but it's the third exam, which remember I dropped the lowest of the first three exams. Okay. And then the following week will be the final. And I really need you to kind of have that exam completed by like Wednesday of that week. Okay. So I'll open it like on Sunday of finals week, which is like May 3rd. And, but you need to complete it by the, hopefully by that Wednesday, if at all possible. It won't be due the following Monday because no, I'll have not the final. I'll have to have grades in. Okay. So yeah, so I can't extend it. No, I'm talking the final. Okay, the final. If you look at the calendar here, right, this is the 20th. Okay, so next week, next Monday is the 27th. That we're gonna do the third three phase then. I'm talking the final you'll have to have done by May 6th. Okay. So the final will have to be done by May 6th. Yeah. So yeah, I'm talking we still got a few weeks here yet, but just trying to give you a look forward of where we're at. All right. So any other questions? Yeah, if you when you go to multi-sim, one of the choices will be a transformer. Okay, and I'll go over that for the lab on Wednesday. Yeah, I'm not on my computer with multi-sim, so I can't show you right now, but I'll show you on Wednesday. I don't remember off the top of my head where it's at. I could look. I got my laptop here. Let's see. It should just be under basic there somewhere, or maybe it's not. I don't remember off the top of my head. Oh, okay, good. Yeah, so transformer. Yeah, it's under basic. Yep. Okay. So yeah, so we'll take a look at that on Wednesday. Okay. And like I said, it'll be a pretty short lab, but and I did record this, so I will post it in case you guys can't